What's up everyone? In this video we're going to be talking about symmetry in different types of polygons. So you probably have heard the word symmetry before, and the reason why I have these little cartoons on here is because there was a TikTok trend that talked about people seeing how symmetrical their faces were. So when we think of symmetry, right, we think about having like that perfect mirror image on each side. In this example here, this would not be a perfect mirror image on each side, right? So we also have symmetry in shape. So there are different types of symmetry, and the first type of symmetry that we're going to talk about is line symmetry. So line symmetry occurs when there is a line of reflection that creates a mirror image on both sides. So to visualize this, we can imagine trying to fold an image as if it was on a piece of paper. So if we physically took these shapes here and folded them over, like what is happening in the GIFs, when we fold them over, the sides should land directly on one another when you fold them over that line. And if they do fold directly onto one another, then we know that that is a line of reflection. So these are some non-examples of lines of symmetry or lines of reflection. So in this heart here, you can see that if this was the line that we were folding the shape over, there's no way that these curved pieces right here are going to fold exactly onto these long pointed edge over here, right? Like that's not going to work. Also, in this example here, we have a curved edge over here. So this is not a line of symmetry because this curved edge is never going to land directly onto this sharp edge on the other side, right? So these are some examples that this course might ask you about. It might say, hey, find two equations of the lines of reflection of the figure below. So lines of reflection are the same things as saying, hey, find the line of symmetry. These are the exact same thing. Now, your equation for this diagram is either going to be perfectly horizontal or perfectly vertical. So if you had a horizontal line of reflection, it looks something like that, right? That is the line of y equals 0. Then another line of reflection I can see is kind of right here, right? We're creating that mirror image on both sides, and that would be x equals 4. Now there can be others, but these are just the two equations that I'm going to use for this example. Now, rotational symmetry is another type of symmetry, and this is when we can rotate a figure about a point, and we either use the center of the figure or a vertex or a corner of the figure, and we try to get it to land or map directly onto itself. So remember that for a rotation, we must always specify how much we are rotating it by, right? How many degrees we're rotating it, and what our center is. So for rotational symmetry, if we have a regular polygon, the minimum number of degrees that it would take us to rotate a figure to get it to map onto itself is always 360 over n. So we have 360 over n equals minimum degrees, right? Now if the polygon is not regular, remember a regular polygon means all sides and angles are congruent. So if we don't know that it's a regular polygon, we cannot use this formula here. So if it's not regular, we kind of have to visualize the rotation and think about whether or not the rotated figure looks exactly like the original figure. So in these examples, we're going to talk about rotating a couple of different shapes about a couple of different points. So we know that to figure out the minimum number of degrees that we can rotate a figure to map it onto itself, we know that we can use 360 over n, right, where n is the number of sides. So here we have a square. Now, the big thing here is that this formula can only work on regular polygons. Now, regular figures just mean that all sides and angles are congruent, right? So we already know that in a square that satisfies that condition, so we're allowed to use this formula here. So from this formula, I know that I need to at least go 90 degrees in order to map the square onto itself. And again, that's the minimum number of degrees, the minimum rotation to carry the figure onto itself. So we're going to kind of see what this is going to look like with some patty paper. So here, I traced out our square, and we're going to be rotating about its center right now. So when we're rotating about the center point is where the needle of our pencil goes. We know that's not going to move at all. So as we rotate, we go counterclockwise, right? We're rotating. We can see that this is kind of like 45 degrees here. Now we can see with the 45-degree rotation, we're not quite there yet. In order for the square to map onto itself, the figures need to land on each other, right? So we have to keep going, and according to my formula, I need to go at least 90 degrees to do that, right? Boom.
There's 90 degrees. So when we go 90 degrees, our figure maps onto itself, and that's great, but there are some other options here. So if I go another 90 degrees, so in total, if we do a 180-degree rotation from our start, I'm also going to map my square onto itself. So let's add 180 degrees to that list, right? Now, if I keep going from my center, so I've already rotated 180 degrees. If I go another 90, boom, 270 degrees, we also map the square onto itself, right? And then if I go another full 90-degree rotation, that's a 360-degree rotation, which also maps the square onto itself. So we can see 90 degrees is the minimum rotation, but any multiple of 90 would work, right? So even if we went another 90 degrees and we did 450 degrees from the start, right? We know that 450 degrees will allow us to map the square onto itself. Any multiple of 90 degrees would work. Now, when we go to a rectangle, our rectangle is a little bit different. So for a rectangle, we are not allowed to use 360 over n. We cannot use that. Now, the reason is this is only for regular polygons. And in a rectangle, we know not all four sides are congruent. So we're not allowed to use this. If you did use it, you might think, oh, I can go 90 degrees, or n would be 4. You might think, oh, I could go 90 degrees. But if you take a look at this, if we rotate a rectangle about the center and we go 90 degrees, you can visibly see that those figures are not landing on one another, right? So 90 degrees does not work. So for certain figures where they're not regular, you kind of got to visualize. So if I go another 90 degrees, which would be 180 degrees in total, we can see that this figure is mapping onto itself here. Now, if we go 270, again, you can see that that's not working, but 360 does, right? So for a rectangle, we have 180 degrees, we have 360 degrees, and then it's going to be any multiple of this 180 would work. Now, for our last example for a parallelogram, same idea. We're not allowed to use 360 over n because there's no guarantee that all four sides and all four angles are congruent, right? So let's just talk about, or let's just see what this is going to look like. So if we rotate a parallelogram about its center, if we go 90 degrees, we end up with something like this, where we see the figures are not matching up. They're not landing on it. It's not landing on itself. If we go 180, we can see that the figure is landing on itself with 180, right? We started here, and then if we rotate 180 degrees about its center, it lands on itself, right? So for parallelogram, 180 degrees works. But then if we go 270, we can see that that does not work. But if we go another 180 degrees for a total of 360, that's going to work. And that 360-degree rotation is always going to work because that's just doing a full rotation around. So if you rotate your figure a full 360 degrees, it's going to end up back where it started.
All right, so let's just do a rotational symmetry example. So it says, which rotation about its center will carry a regular decagon onto itself? So this is where the names of the shapes are going to pop up again. So we know that in a decagon, that's 10 sides right there. So to find the minimum number of degrees, we do 360 over n is going to equal that minimum rotation. So we do 360 over 10. We get 36 degrees. But if you take a look at these choices, 36 is not listed, but remember, any multiple of 36 will work, right? So any multiple will map our figure onto itself. So we got to take a look and see in the answer choices which of these is a multiple of 36. If you take your calculator and you just test these out, 54 does not work. If we do 162 divided by 36, we get 4.5. That doesn't work. If you do 198 divided by 36, you get 5.5. That doesn't work. But if we do 252 divided by 36, we get 7. So that's the only one where 36 can be divided into. So that's the only answer choice that works there.
Now for this portion, we're just going to talk about what it looks like to rotate a figure about a vertex. So remember that a vertex is just any corner here of the shape. So if we're rotating about our vertex, if that's the center, then we're keeping our pencil there. That's the point that's going to stay the same, and then everything is rotating about that, right? So if we pick this vertex here and we rotated our figure around, we can kind of get a nice picture of what's going to happen here. So when you're rotating about a vertex, though, you have to go that full 360 degrees for the square to map onto itself. Now, even if we picked a vertex, like let's say we pick this top left one here, when we go 90 degrees, we see what happens here all around, right? And again, that full 360 degrees is needed to map this figure onto itself. Now we can do the same thing for a rectangle, right? It's going to pretty much look the same as a square, so I'll just do it for one. So if we pick this bottom left vertex here, this is what it would look like when we rotate about a vertex. And again, you need that full 360 degrees to get there. And then last but not least, for parallelogram, we can kind of do the same thing. And again, it doesn't matter the vertex that you choose. It's going to be the same exact idea. So let's choose a different one. This is going to end up off the grid, but that's okay. So we choose this vertex as top right one. So if we go 90 degrees, 180, 270, and 360, again, we need that full 360 degree rotation in order for our figure to map onto itself.
All right. So those are the two different types of symmetry that we're going to be talking about in this class. So we have line symmetry and we have rotational symmetry. Now for rotational symmetry, make sure that you know that formula of 360 over n equaling the minimum degrees rotation. And we are either rotating about a center or about a vertex.